All right, if you haven't seen the other video on bonding and determining a basic Lewis formula for an element or just a basic element on the periodic table, then you should go back and watch that video on my web page. All right, so this is the second half of the video, and essentially what we're doing is we're determining Lewis formulas. So we are going to look at determining a Lewis structure formula for a compound. So the first thing we need to do is count the valence electrons in an atom by adding the valence electrons of each atom. All right, so the example we're going to try right now is sulfur trioxide, or SO3. So we need to first count the number of valence electrons in each atom by adding them up. So in sulfur, I have 6 valence electrons. So I have 6 valence electrons, so I'm going to put that in just on the side here to keep track, and O3. So I have 3 oxygens, and each oxygen will have, again, 6 valence electrons, so making a total of 18 valence electrons here. So when I add these up here, I get 24 valence electrons total. All right. So that's the first step, is just to count the valence electrons in the atom by adding the valence electrons of each atom. So then I need to arrange the peripheral atom symbols around the central atom symbol and place a pair of valence electrons between the peripheral atom and the central atom, or to make these bonding pairs. Now what that means, now in this case with sulfur trioxide, I'm going to use sulfur as my bonding my central atom. All right, so let's go ahead and do that. Just gonna, okay. So I'm gonna make sulfur my central atom. And I'm gonna arrange the peripheral atoms around the central atom and place a pair of electrons between each of these. All right. So I'm going to represent the electrons given by sulfur by a blue X, and the electrons from oxygen with a red dot. It really doesn't matter how I represent them, just as long as we have a bonding pair between each of the atoms. So my sulfur atom, here is my central atom. Because I do have 3 oxygens surrounding it, although the bonding capacity, which is how we determine what is usually our central atom, is the same between oxygen and sulfur. Okay, so step number 3. Again, remember, you can pause this video at any time in order to take the notes and write down the steps of the procedure to make sure that we're on the same page here. So step number 3, it says place more pairs of valence electrons or lone pairs on the peripheral atoms to complete their octets. So essentially we like to have atoms with complete octets, or 8 electrons around each atom. Okay, but in terms of molecular compounds, this is where we have covalent bonds, so we share electrons between the atoms. So I've only used up 2, 4, and 6 electrons of my 24, which means I have 18 electrons remaining. So I'm going to go ahead and, with my remaining electrons, I'm going to just do these in another color, it doesn't really matter. I'm going to go around each oxygen atom, filling in my other 18 electrons remaining. So I have 6 there, 7, 8, 9, 10, 11, 12, 13, 14, oops, 15, and all right, 16, and 2 more at the top here, 17, 18, whoops, sorry, it's kind of ugly. It's challenging to draw on this computer pad. All right, so if you count my electrons with including the green, blue, and red, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which is the total amount that we had counted up at the beginning. Now, as you notice, each oxygen has a complete octet. It has 8 electrons surrounding it, which means that it is a happy atom. All right. Now, any remaining valence electrons can be added onto the central atom as a lone pair. Well, in this case, we do not have any extra valence electrons. Now, as you'll notice, sulfur does not have a complete octet. So if it says, if the central atom's octet is not complete, what we need to do is we need to move a lone pair from a peripheral atom to a new position between that peripheral atom and the central atom. We repeat this until it has a complete octet. So what I mean by that is we are essentially going to, I'll use a nicer orange there, we're essentially going to shift one pair of a lone pair from an oxygen peripheral atom, and we're just going to put it as a new bond in between. All right, so essentially we're moving these 2 electrons in between the sulfur and the oxygen to make these ones shift over. So I'm just going to erase these here, and when I do that, I'll redraw them where they need to be. All right, go back to green here. All right, so essentially what happened is these green electrons just shifted in towards the middle. All right, now by doing that, because our electrons can be shared, they're covalent, it's a molecular compound, which means we're sharing all of these electrons. Okay, when that happens, I can just create what we call a double bond. So we have twice the amount of electrons stored between these 2 atoms, but because they share them, they can each be counted towards each individual's octet. So this oxygen atom has 2 lone pairs here, and then 4 bonding electrons in between the sulfur and the oxygen. Same with the sulfur, we have bonding pair here, a bonding pair here, and a double bonding pair between the sulfur and oxygen. So they each have their own octet. Even though there is an overlap between, they get to share those electrons. All right. Then we need to consider if an entity is in a polyatomic ion, we place square brackets around the Lewis formula and write the net charge outside the brackets. So just remember here that if an entity is a polyatomic ion, we subtract valence electrons from to account for its net charge. So when we go back to our example with NH4, let's just take a look, and I'm going to erase this. When we look at NH4, so each hydrogen atom can carry, change this back to black. All right, each hydrogen atom can carry 1 electron, which means that hydrogen has 4 electrons because we have NH4, and nitrogen has 5. All right, so that makes for a total of 9 electrons that we can have between the nitrogens and the hydrogens. Now, the trick is NH4 is positive, which means we have to account for the loss of a single electron. So we're going to actually subtract 1 here, and we're going to get 8 electrons that we can use to create our Lewis formula for NH4. So I am going to start with my nitrogen in the middle. All right. And how do I know nitrogen is my central atom? I know nitrogen is the central atom because it has the greatest bonding capacity. It has bonding capacity for 3 spots for hydrogen to be attached to, or it has a greater bonding capacity. So when we go ahead, we're going to go ahead by putting our hydrogens around our nitrogen. Okay. Perfect, just like this. Okay, now we have 8 electrons to distribute between our um, our atoms here. So again, this is where we just go and we look at putting a pair between our atoms of our central atom and our peripheral atoms. So if I put a pair between each of these, to create a bond or a bonding pair, which these two electrons will just turn into a single bond around each H or each hydrogen. Okay, I've used up all 8 electrons. So usually I would have an extra electron, but because our net charge is +1 with ammonium, I simply put square brackets around my polyatomic ion Lewis diagram and add a positive sign on the outside of those brackets. All right, so I'm just gonna get rid of the kind of this garbly goop on the side. All right, so this is what my net result looks like. I have my nitrogen as my central atom, my 4 hydrogens as peripheral atoms, each with bonding pairs in between, and a net positive charge outside of my square brackets. All right, I have other examples here that we can try. Let's take a look maybe at, we'll take a look at phosphine and hydrogen sulfide really quickly in my example. And I'll just remind you again that I have provided you with some note packages that have some more examples of how to work through these Lewis structure formulas. All right, so let's start with phosphine, or pH3. So we start with P. P is going to be our central atom. I know that because it has the greatest bonding capacity. Hydrogen only has the bonding capacity of 1, making it very challenging to make as a central atom. So when I add these all up, phosphorus has 5 electrons. Each hydrogen has 1, which means that we have 3 electrons to account for there. Total of 8 electrons to deal with when we are balancing or trying to create this Lewis structure. Now, notice that phosphine is not a polyatomic ion, so there is no net charge, so we can simply just place our hydrogen atoms around our phosphine, or phosphorus, pardon me, to make phosphine, just like so. All right, so I have 8 electrons to deal with. Now, again, remember that we have to start by putting electrons between our bonded atoms. So I have a pair of electrons between each hydrogen and the phosphorus central atom, like so. So right now what I've done is I've dealt with 6 electrons. I've used up 6 electrons for each bonding pair, leaving me with 2 electrons remaining. Okay, so when I have 2 electrons remaining, my rules state that we arrange the peripheral atoms and symbols around that central atom, and we put 1 pair of valence electrons between those atoms. If we have more valence electrons around the peripheral atoms to complete their octets, which we don't need to worry about with hydrogen in this case, because hydrogen has a complete octet with 2 electrons. All right, we do not require hydrogen to have more than that because it only has 1 energy level with 2 electrons. Okay, so once I deal with that, we have any remaining valence electrons are dealt with by placing them as a lone pair around our central atom. So if I was to do that, I would simply just have a single lone pair, as we see here in green, which accounts for our 2 extra electrons. All right, so this is what our phosphine molecule would look like as a Lewis diagram. So we'll take one more look at hydrogen sulfide. And I'm just going to quickly draw it for you. And that is all for the day. So once I finish this, I would like you to quickly just take a look at your other video that is from the Crash Course series, and it is linked to my teacher page. So once I'm done with this drawing, you can just take a look, do some checks, and you'll be done for the lesson portion, and then just take some notes and do some examples. All right, so here's what your last Lewis structure of hydrogen sulfide would look like, and don't worry too much if you're still stuck on going through this. I'll be able to help you out on Monday. All right, that's it for now, and good luck with everything. See you Monday.